Dear friends, today we want to have fun using water. We have a box full of water and a wooden ball. Normally the ball is floating in the water, but this time we want to let this ball falling inside, and we meter how deep is sinking by leaving it fall at different heights, and we check if there is a difference and what the difference is depending upon. And for doing that we use our tape meter and a slow motion video. Let's have fun together. The experiment is the following. We have a water pot and we drop a ball from different heights, 140, 180 and 220 centimeters respectively. The water level is known, 25 centimeters, as well the mass and the size of the ball. We want to meter how deep the ball is diving in the three cases, and finally what is the height needed to get the bottom. First experiment. The ball drops from 140 centimeters The achieved depth is 18 centimeters and the diving time 1.02 seconds. Second trial. The drop height is now 40 centimeters more. Here we get 19 centimeters instead, so 1 centimeter deeper, and the diving time is 1.07 seconds. Finally, the third experiment, where the dropping height is 2.2 meters. Still deeper, another centimeter, and the diving time is only 1.09 seconds. Very small changes. Now we want to understand why. We have at disposal the laws of the mechanics. The first dynamic law says that the mass times acceleration is equal to the sum of the external forces. But which forces are there? We have the weight, the buoyancy, the friction, capital F, and the drag, capital D. We can express now each one of them. The weight is always the mass times the gravity factor. The buoyancy is equal to the volume of the sphere times the water density and the gravity factor G. And this force is opposite to the weight, therefore negative. We take as positive the axis X towards up, like in the picture. And then we have two more forces, the one in red. Both are depending upon the speed and opposite to it. The friction F is equal to this formula, which is given by the Stokes law, and is proportional to the speed and to the viscosity of the medium μ, and also depending upon the sides R. And the last force is the drag, which is proportional to the velocity square, the density of the medium, so rho W, the cross section A, and its shape by means of the drag coefficient CD. We will see this topic in detail afterwards. If we write the equation by considering that the volume of the sphere is 4/3 pi r cube, we got this expression, and we can simplify the quantities present both left and right side, and neglecting the friction in comparison with the drag, since the viscosity of the water is very low, we will get this expression. That is a simplified expression that we solve for acceleration. And now we need to approach a numerical method. First, we write the initial conditions. For t equals 0, the space is 0, and the velocity is given by the energy conservation law, that is square root of 2 times g times the distance to the water surface. The acceleration can be found using the formula on the right side, just replacing the initial value of v. Once the acceleration is known, then we can find the velocity at the next step, which is v1, adding the velocity at the step before v0 plus acceleration times delta t. the new displacement x1, we can also determine, starting from the displacement at the step 0 plus v1 times delta t, and so on. We have found the solution method. Now we need to implement it. What are missing are the parameters of the experiment, of course. Here we are. The ball size is 24.8, the diameter. Its mass 7 grams. The density of the water and the level of the pot are also given. The heights of the falls are different by each experiment, and consequently it changes the initial velocity, the velocity when the ball is touching the water. The drag coefficient is not a constant. Instead, it depends upon the Reynolds number. In our case, its value for the first experiment and starting velocity is 1.2 10 to 5 dimensionless. By means of an empiric formula, we can get the value 0.44 here displayed. And we observe that this value is practically constant up to Reynolds 10,000. And for make it simple, we take this value constant not only within the single experiment but also for the following two. Once the corresponding values are calculated, then we can start the iteration process. Let's see now the first example where the height is 1.4 meters and we take for delta time 1,000th of second and the maximum number of 1,200 steps. From the initial conditions we can fill the first row, that is step 0. The second row of the table shows how to fill the step number 1 and the next ones. The time is simply the product between the step number and the delta t here. The displacement and the velocity are explained in the first slide, as well as the acceleration formula, which is using now the velocity already calculated in the same step here. And then we can proceed till when the displacement becomes 0 again, our body raised back to the water surface. The corresponding time is the diving time, and to find the maximum depth is enough to identify the time when the velocity is 0 instead. Let's represent now the solution in the chart. The velocity is a red curve and the displacement a blue one. Velocity is always increasing, actually decreasing in absolute value since of negative sign, up to the point where the maximum depth is achieved, this point, and then is increasing back up to the limit value. On the other hand, the displacement is decreasing from the 0 level up to the maximum depth and then raising linear as far as the velocity is constant. Where the displacement is becoming 0 again, the diving time is achieved. If you repeat the simulation for the experiment 2 and 3, we notice that they have very similar behavior, but the maximum depth increases as well as the diving time, but not much. Another important observation is that the time when the maximum depth is achieved is also not changing. We resume here in the table the comparison between the simulation and the experiment values, and we notice that for the depth practically there is no deviation. The simulation is matching perfectly. And for the diving time, the simulation is giving a slightly less time, maybe due to the accuracy of the slow motion, whose resolution is only 1/8 of a second. The last question we need to answer is, which is the dropping height needed to reach the bottom of the water pot? We apply the same equation and its numerical solution, but we are changing h till when the depth becomes our set value, that is 23.8 centimeters. This is the depth minus the radius of the ball. And we find 8.1 meter. That is really a lot. The diving time instead is not changing significantly. we get 1.3 seconds. Eventually we have checked that what happening is not intuitive at all. We would have expected the higher is the ball, the deeper is sinking. Actually, it is very little difference, and we explained why. Thanks for attention. See you next time.